Today we start a long series of videos on chemical equilibrium. It's going to cover a few chapters in the Zumdahl book, and this first few videos are just an introduction to the basic ideas of chemical equilibrium and a little practice in some of the special calculation strategies that are helpful in doing equilibrium calculations. And then we'll get into some particular kinds of equilibria that are relatively important in different branches of chemistry. We're going to start this out by thinking about a reaction occurring. And this is the kind of reaction that could reach dynamic equilibrium, a reversible reaction. In this reaction, HI is decomposing, take 2 moles of HI, to produce H2 and I2. And all three of these species would be gases. So initially, let's pretend that we have some amount of HI. Call it HI naught, doesn't really matter what the quantity is, but we don't have any H2, we don't have any I2, no products at first. We're plotting here on this graph concentration versus time, and as we saw in the kinetics videos, at first we're going to see a rapid loss of HI. The initial concentration of HI will decrease pretty quickly at first, but as concentration drops, then we see that rate also slows down, and so the slope of this curve gradually begins to change. The same thing will be happening for the products, only in reverse. At first we have 0 H2 and we have 0 I2. But then, at first, initially we'll see a steep increase in the amount of H2 and I2 that are present, and then gradually they'll be produced at slower and slower rates as the reaction rate goes down. And so we'll have this converging sort of a pattern, and eventually we'll reach dynamic equilibrium. So this reaction will become reversible. What's going on after about this point, we're at dynamic equilibrium, the forward and reverse rates are exactly the same, and so the concentrations of reactants and products become constant in this zone right here. Now it turns out that at dynamic equilibrium there's a relationship between the concentrations of the reactants and the products, and chemists were interested in figuring out if there was some way to predict this and what exactly the pattern was. So we're going to take a look at 3 different experiments like this one and see if we can track down the equilibrium mathematical model. So in this experiment we start out with an initial concentration of HI that's 0.20 moles per liter. We don't have any H2 and we don't have any I2. Only reactants to begin. When we finally reach equilibrium, this is what's found with this experiment. If you start out with 0.2 moles of HI, no products, you end up with 0.160 moles of HI, and the concentration of H2 and I2 will both be 0.020 moles. We would expect the concentration of H2 and I2 to both be the same because the stoichiometry is 1 to 1. Here's another experiment. Only in this one we're doing backwards. We start out with no reactant, no HI at all, but we have 0.3 moles of H2 and 0.3 moles of I2 to begin. When we do it this way, we find out that at equilibrium we have 0.480 moles of HI and we have 0.060 moles of both H2 and I2. So the concentrations of the products have gone down, the concentration of reactants have gone up, but they reach a steady state. They reach dynamic equilibrium, and then the concentrations become constant. Here's a third experiment. In this case, we start out with some of each, 0.1 mole concentration of HI and H2 and I2. When we finally establish equilibrium, we have 0.240 moles per liter of HI and 0.030 moles per liter of the 2 products, the H2 and the I2. Now, let's look at how these would graph out on a time versus concentration graph, and then let's start to look for a pattern. This is the whole chart put together with everything, all the 3 experiments on it. We're going to move to a new workspace and see if we can find out what the pattern is, if there is one. Well, I'm going to first examine experiment number 1. Experiment number 1, here's my graph of time versus concentration. And in this graph, I'm going to make HI concentration in red. So my initial concentration of HI starts out at 0.20 moles per liter, and it drops, and by the time I reach equilibrium, the concentration of HI has gone down to 0.160. I'm going to make the I2 concentration in blue. Concentration of I2 originally starts out at nothing, and it rises until when we reach dynamic equilibrium, it is at 0.020. And in green, I'm going to put the concentration of H2, and it follows exactly the pattern that we saw with I2 concentration. Starts at 0 and ends up at 0.02. Dynamic equilibrium occurs right in this zone. After we get past this point, we're at equilibrium. Next, I'm going to look at experiment number 2. And again, I'm making a graph of time versus concentration. Now my HI concentration starts out at 0, and it rises until at dynamic equilibrium it's at 0.48. My I2 concentration starts out at 0.3, and it drops until at dynamic equilibrium it's finally at 0.06. H2 concentration follows that same pattern, starts at 0.3 and ends at 0.06. Experiment 3. Another graph, time versus concentration. Here all three of them start at the same point, and that is 0.100 moles per liter. Only what happens to them when they reach dynamic equilibrium is very different. The concentration of HI rises until at dynamic equilibrium it is at 0.240. The concentration of I2 starts at 0.10 and it drops until when it reaches dynamic equilibrium it's at 0.030. And of course, as we've seen, the concentration of H2 is going to follow that same path and end up at dynamic equilibrium also at 0.030. So here's equilibrium after this point, and here's equilibrium after that point. Now let's start to look for a numerical pattern. Looking at experiment number 1, I'm going to set this up as a ratio of product concentrations to reactant concentrations and see if they're consistent. So for experiment number 1, at equilibrium I have 0.020 times 0.020. So I'm taking concentration of H2 times concentration of I2. And I'm going to divide it by the concentration of HI and just see if this is a consistent ratio. And that was 0.160 for this experiment. When I do the multiplication and division here, work this all out, I get 0.0025. Let's see if I get the same result when I try that same ratio for experiment number 2. In experiment number 2, my product concentrations at the end were 0.060. So I'm going to multiply 0.060 by itself because there are two products. And then I'm going to divide by 0.480 because that was the concentration of HI at equilibrium. So essentially what I'm trying to do is develop a ratio that will tell me how far does this go to the right, how much product is produced, what's the ratio of product to reactant when it reaches dynamic equilibrium. If I do this arithmetic, I get 0.0075. Well, that's not the same number. Let's try experiment number 3. At dynamic equilibrium, here were the ratios. 0.030, both of the products had that concentration. And the reactant had a concentration of 0.240. If I do this arithmetic, I get 0.00375, which is different from both of the other two. So clearly that ratio is not anything constant that we can use as a pattern that would allow us to predict concentrations at equilibrium. Well, here's another thing we could try. What if we raised them to their coefficients? Because maybe stoichiometry has something to do with this. So the balanced equation in this reaction is 2HI decomposes to I2 plus H2. Let's try that same ratio, only we'll raise the HI concentration to the second power. So for experiment number 1, that would be 0.020 times 0.020. Those will both be raised to the first power because the coefficient is 1 on both of those products. Divided by 0.160, but we're raising this to the second power because it's coefficient is 2. When we do the calculation, we come up with 0.016. Now let's try that for experiment number 2 and find out if we get the same result. Experiment number 2, we had final concentrations of 0.060 for both of the products. Those would be raised to the 1 power. And then 0.480 was the final concentration of our reactant species, and that would be squared. When we do this calculation, in fact, we do get 0.016. Let's see if it works in every case. For experiment number 3, we'd be taking 0.030 times 0.030, and we'd be dividing by 0.240 squared. And this gives us 0.016. So there's a pattern here. When you take the concentrations of reactants and products, and you put the reactants on the bottom, products on the top, and raise them to their coefficients, then you get a consistent, predictable pattern that will allow you to figure out how much reactant and how much product will be present when you finally reach dynamic equilibrium. In other words, it tells us how far does the reaction go when it reaches that point where we recognize that it's in dynamic equilibrium. So let's generalize this. For a reaction that's occurring between gaseous or aqueous species, and that's important, solids and liquids don't really have concentrations, and they don't affect equilibrium. Here's our generic equation. A and B are reactants, C and D are products, and their coefficients are little a, little b, little c, and little d, respectively. We have a thing called the equilibrium constant, which is called Kc. For a generic reaction between gaseous or aqueous species A, B, C, and D, this is how Kc can be evaluated. The equilibrium constant is equal to the concentration of products, C and D in this case, raised to their coefficients, little c and little d, divided by the concentrations of reactants, A and B in this case, raised to their coefficients. And that should give us a consistent, predictable way to determine how far the reaction goes before it reaches equilibrium. So once again, terms for solids and liquids do not appear in this definition. So let's take a look at this particular reaction. What would Kc be for this reaction? I'm not looking for a number here. Instead, I'm looking for an expression. How would we write it? Well, calcium carbonate is a solid, calcium oxide is a solid, but CO2 is a gas, and that would be included in Kc. So Kc is equal to concentration of CO2 raised to the 1 power. And that's it. It's not divided by the reactant because the reactant is a solid. Before we go on, I'd like to point out that if you're not at equilibrium, you can still use that expression for the ratio of products to reactants raised to their coefficients as a valuable description of where you are at. But it's not called Kc if you're not at equilibrium. Instead, it's called the mass action expression or the reaction quotient, and we give it the label Q. You'll hear more about that later on when we start to make predictions about whether or not we're at equilibrium. It turns out that if you know K for a certain reaction, you can manipulate the reaction, turn it around, change the coefficients, and predict what K is going to be for the resulting change. So here's one example. If we had N2O4 in equilibrium with two NO2s, and Kc for that reaction at a certain temperature is 0.036, we could figure out what Kc would be if we cut all the coefficients in half. So in other words, for 1/2 N2O4 in equilibrium with 1 NO2, what would K be? Well, let's look at the expression for Kc. Kc really is concentration of NO2, whatever that is, squared divided by concentration of N2O4 raised to the 1 power. Now that square term comes from the coefficient 2 in front of NO2. Now in the new equation, I don't have that anymore. The N2O4 had a coefficient of 1 in the old equation, but now it's a coefficient of 1/2, so I'd have to raise this to the 1/2. What I've effectively done is I've taken the old K and I've taken the square root of it. So NO2 squared over N2O4 to the 1, I take the square root of it, and I have the new K expression. So Kc for the new is always equal to the nth root of whatever I did to the coefficients in terms of dividing. So in this case, I divided by 2. I divide all the coefficients by 2, so I take the square root of 0.36, and that's my new K expression, 0.60. But if I had divided them in thirds, then I'd take the cube root. If I had divided them in fourths, I'd take the fourth root. So, in general, we can say that Kc for the new expression, if you divide by m, so divide by m on all the coefficients, the new Kc is going to be the nth root of the old Kc. Let's look at this case. If I start out with the same equation that I had before, and now I double the coefficients, so 2 N2O4 is in equilibrium with 4 NO2s. What's happened here is, in terms of the Kc expression, I used to have NO2 squared divided by concentration of N2O4 to the 1, but now I have NO2 to the 4th divided by concentration of N2O4 squared. So what I've done is I've taken the old expression and I've squared it. So to generalize, if I multiply by m, my coefficients, the new Kc is going to be equal to the old Kc raised to the m power. Here I square it because my coefficients are doubled. If I had tripled them, I'd cube it. One more example. If I take this equation and write it backwards, so it's 2NO2 in equilibrium with N2O4, what happens to my Kc expression? Well, it's always reactants over products. So before, it was concentration of NO2 squared divided by concentration of N2O4 to the 1 power. Now it's just the opposite, N2O4 over concentration of NO2 squared. So I've taken the reciprocal. So if I reverse the reaction, the new Kc is equal to 1 over the old Kc. So in this case, it would be 1 over 0.36. The next thing we'd like to look at is what happens if you can sum reactions up. Like we saw that you can add together reactions when we were working with Hess's law, and we also saw it when we were adding up elementary processes in reaction mechanisms. What about reversible reactions that can be summed together? What's the K for the sum of two reactions? Well, let's think it through. For this first reaction, K could be expressed this way. Kc is concentration of NO times concentration of O divided by concentration of NO2. For this second reaction, Kc is equal to concentration of NO2 times concentration of O2 divided by concentration of O3 times concentration of NO. What would be the sum of the two reactions? Well, NO2 would cancel out, and so would NO. It's on both sides of the arrow. So that would leave us with O3 reversibly decomposing to O plus O2. Well, Kc for that reaction would be concentration of O times concentration of O2 divided by concentration of O3. How is this related to the two previous Kc's? Watch what happens when I put them right next to each other. Going through here and canceling out things that appear on both top and bottom, I have NO2 canceling out and NO canceling out. What's left is O concentration times O2 concentration divided by O3 concentration. So I can get the Kc for the overall reaction by multiplying together the Ks for the individual reactions. So for this reaction, remember this summed up to O3 gas decomposing reversibly into O gas plus O2 gas. Kc for this reaction would be the product of 6.8 times 10 to the negative 49th times 5.8 times 10 to the negative 34th. In general, this is called the rule of multiple equilibria. The rule of multiple equilibria says that if reaction 1 plus reaction 2 add up to reaction 3, then K for reaction 3 is equal to K1 times K2. We've seen how we can express equilibrium situations in terms of concentrations of reactants and products. Can we do this in terms of partial pressure? Let's think about pressure. Pressure, remember, is equal to N times R times T divided by V. But if you're measuring your volume in liters, N divided by V is molarity, so pressure is equal to molarity times R times T. Or we could say molarity is pressure divided by R times T. So the concentration of any reactant or product A could be expressed as the partial pressure of A divided by R times T. So if I have my generic reaction, AAs plus BBs, in reversible equilibrium with CCs and DDs, then Kc for this reaction, which is concentration of C raised to the C times concentration of D raised to the D over concentration of A to the A times concentration of B to the B, could be rewritten this way. Partial pressure of C over RT raised to the C times partial pressure of D over RT raised to the D over partial pressure of A over RT raised to the A times partial pressure of B over RT raised to the B. Each one of these terms here has got the reciprocal of RT in it, so we could pull that out, factor that out of this. So this comes down to PC to the C times PD to the D over PA to the A times PB to the B times 1 over RT raised to the C plus D minus A plus B. But 1 over RT is a constant if temperature doesn't change. And when you raise a constant to any exponents, you just get another constant. So we could say then that Kc is equal to another constant, let's call it K primed, times Pc to the C, Pd to the D, over Pa to the A, times Pb to the B. So if we take Kc and divide by this K prime, we get a different constant. Let's call it Kp for pressure, and it's equal to Pc to the C times Pd to the D over Pa raised to the A power times Pb raised to the B power. That equilibrium expression can be used when you have only gaseous reactants. Another thing that might be useful is to be able to convert back and forth between Kp and Kc. So let's explore how that might be done. So for our generic reaction, where AAs and BBs react reversibly to make CCs and D moles of D, we know that our Kp, if these are all gases, all of these have to be gases for this to work, Kp would be partial pressure of C to the C times partial pressure of D raised to the D over partial pressure of A to the A times partial pressure of B raised to the B. But remember, when we were developing this, we found that Kc was equal to 1 over RT raised to the C plus D minus A plus B times Pc to the C times Pd to the D over Pa to the A times Pb to the B. So that could be replaced just with Kp. Now let's look at what makes a difference in a real chemical reaction that doesn't necessarily always have everything being gases or the same number of moles of gases. Like, let's look at this one. If I have N2O4 gas in interaction with 2NO2 gas. On the right-hand side, I have 2 moles of gas. On the left-hand side, I have 1 mole of gas. So in this real situation, that 1 over RT would be raised to the 2 minus 1 mole of gas. Since we're only interested in gases here, that difference that we're looking at, in this case, which is 1, that's really equal to the change in number of moles of gas, because only gases are important in this expression. So instead of C plus D minus A plus B, since we're only interested in gases, we can replace this with the change in number of moles of gas. So we can simplify this as Kc is equal to 1 over RT raised to the delta N of gas, change in number of moles of gas, times Kp. Or another way of writing it, if we wanted to convert the other way, we could say Kp is equal to Kc times RT raised to the change in number of moles of gas as you go from left to right. So that expression can be used to go back and forth between Kp and Kc. The R that you'd be using here is the 0.0821 liter atmospheres per mole Kelvin.